In this diagram, you have a charged particle on the left, and you've got two metal plates which are also charged on the right here. Around these, you'll find an electric field pattern like this. So an electric field is a region in space in which a charged particle would experience a force. So for example, if I put another positive charged particle over here, it would be repelled by the positive charge in center. So it would be a force away point like this. And if I put a negative charge over here, for example, then it would be attracted towards the positive plate and repelled away from the negative plate. So an electric field points in the direction of positive charge would experience a force. But on the left-hand side, we have a negative charge, so that's why it's going in the opposite direction, the direction of the field. The electric field strength, which is given capital E, at a point in a field is defined as the force per unit charge on a positive test charge placed at that point. So you can use this equation here where F is the force in newtons, Q is a charge in coulombs, and therefore the electric field strength, which is capital E here, is measured in newtons per coulomb. You can also use lowercase q for charge if you want it. In this example, a +2 ion is placed at point X. The electric field strength at point X is 4 times 10⁸ newtons per coulomb. Calculate the force on the ion. Okay, so we've got the electric field strength, which is the newtons per coulomb, the force per unit charge. So if we multiply by the charge that we've placed at X, we can get the force. So we times it by 2 times 1.6 times the power of -19, because we have to use actual charge, not just a relative charge. So we get the force here. Basically, we've just used this equation where the electric field strength times the charge gives us the force, the electric force. Okay, in example 2, an electron is placed between two charged parallel plates. Calculate the electric field strength needed to give the electron an acceleration of 3 times 10 to 12 meters per second squared. So please don't mistake this acceleration with speed. It is not traveling at this speed, that's the acceleration. So it has to be accelerating for long enough to reach anywhere near a speed of 10 to 12 meters per second. It won't, because that's faster than the speed of light. Okay, so we need to calculate the electric field strength, and we've got an acceleration. But what we need to do first is calculate the electric force required to get this acceleration. To do that, we can use F equals ma. So m, the mass of the electron we can get from our data sheets, which is 9.11 times 10 to the minus 31 kilograms, times it by the acceleration that we're trying to get. So that gives us a force that we need. This force, which is the only force acting on this electron, is going to be provided by the electric field there. So we can use the equation for electric field strength, force over charge. So we've got the force, and we know the charge of an electron as well, which is 1.6 times to the power minus 19. So that gives us the electric field strength required to get this acceleration. These particles here have an electric field pattern around them. This is what we call a radial electric field pattern. This is the pattern that you get around point charges or particles. So, but we can also use them for other objects which we can treat as point charges. And the field direction of the field here points in the direction a positive charge would experience a force. So for example, if I put a positive charge here, it would be pushed away from the other positive charge. So it's gonna move, basically, or it's gonna accelerate in the direction of the field lines there. If I put it over here, then it will be attracted towards the negative charge. So again, it's going to accelerate or experience a force in the direction of the field lines. However, if I put a negative charge in that field, then it's actually going to move in the opposite direction to the field lines. So it's going to be attracted towards the positive charge like that. And if I put a negative charge over here, of course, it moves in the opposite direction, the direction of the electric field line. So the electric field lines point away from positive charges and towards negative charges. Okay, and finally, the closeness of the field lines indicates the strength of the field. So as you can see, the closer you get to the charge, the closer the field lines are to each other. So that means the closer you get to the charge, the stronger the field. This pattern here is what we call a uniform electric field pattern. And you can get this between charged parallel plates like the one shown in the diagram. We can also get this pattern if you zoom in into a radial field over very small distances, or you can get them near the surface of long flat surfaces. Okay, and again, the direction of the field lines point in the direction a positive charge would experience a force. So if you look at the bottom of the diagram here, the positive charge is experience force in the direction of the field lines, while at the top there, the negative charge is actually experience force in the opposite direction of the field line there. It doesn't mean they'll move in this direction, because if they have some momentum, let's say upwards, then they would continue with that momentum upwards as well. That wouldn't be affected. Again, the closeness of the lines indicates the strength of the field. Here, the distance between the lines is constant, it's the same across. So that means the field strength is the same everywhere inside this uniform field. So for example, at this point, if it's 200 newtons per coulomb, then over here it's 200 newtons per coulomb, and over here is 200 newtons per coulomb. It's the same strength across. However, the very edges, the field starts to bend a bit like this. So in this case, towards the edges, the field pattern, the field strength gets a bit weaker.